Lesson number 9, activities. We will find the derivative of x cubed over x squared in two ways. First, we'll simplify and then take a derivative. So let's do that here. So d over dx of x cubed over x squared is exactly the same as d over dx of, and if we simplify this fraction, we just get plain old x. And then the derivative of x is just the coefficient of x, which is 1. And that's it. That's the answer. That is the correct derivative of this expression. Now we're going to do part B. We'll take a derivative by using one of our new rules. This thing here is a quotient, one function of x divided by another function of x. So we are allowed to use the quotient rule. Now, nobody in their right mind would use the quotient rule on this one, because for sure it's simpler to do what we did in part A, but we're practicing with our new rule, and we will also be comforted, hopefully, when after applying the quotient rule, we get the right answer, which we for sure know is 1. So I'm just copying the original problem here, take a derivative of this thing. So quotient rule says big fraction divided by the bottom squared. So x squared squared. And then in English, bottom, copy the x squared times the derivative of the top. The derivative of the top is 3x squared minus the top, copy the x cubed times the derivative of the bottom, that's just 2x. Now that doesn't look like the right answer, which is 1, but maybe if we clean it up, we'll get there. So the bottom, x squared squared is x to the 4th. You multiply those powers. And now we're going to combine the different factors on the top. X squared times 3x squared is 3x to the 4th. You add those powers, that's an addition, whereas the property on the bottom was multiplication, minus, and then x to the 3rd times 2x. Again, you're adding the powers and you get 2x to the 4. And so upstairs, combining like terms, we just get a single 1x to the 4 divided by the x to the 4, and lo and behold, we get the right answer of 1. Again, I am not proposing that we do the quotient rule on problems that look like that. Simplify before you do derivatives. That's a general good rule of thumb, but it was good practice for us. Okay, number 2. Vertical line divides this rectangle into two pieces. We're going to find the value of x that maximizes the product of the two areas, and we're going to make sure we use one of our new rules here. Okay, so if we look at this picture, we're thinking of the bottom line here as being the x-axis with 0 here at the far left and 1 here, and just a generic x that can move. This x could be anywhere between 0 and 1. And so what does that x mean? It means that the length of this line segment right here, that's the x, and it means that the length of the rest of it, let's use a different color there, the length of the rest of it is 1 minus x. And so that means that so we're looking for the product of the two areas. So that means that the product, let's see, product of the areas is equal to, so let's find the area of the left-hand rectangle. So that's this thing right here. So the base of that rectangle is x, and the height of that rectangle is 2. And so the area of this piece is simply 2x. And then the area of the other side, this rectangle, so in this case, the base is 1 minus x, and the height is also 2, so the area of that one is 2 times not x, but 1 minus x. So now I've got in black and purple my two areas, 2 times 1 minus x. And so we're trying to maximize the product, so it sure feels like we should multiply these two areas right now. So one area was just 2x, and the other area was 2 times 1 minus x. Just to clean this up a little bit, let's distribute the 2. So copying the 2x and distributing the other 2, we get 2 minus 2x. Now definitely we should distribute that 2x, and then it's just a nice looking polynomial with an easy derivative, but I'm saying that I don't want us to distribute there. I want us to actually practice with the product rule here. So let's leave it in the current form and calculate the derivative, p prime, using the product rule. There's an implied multiplication right there. So our product rule says first, so we copy that one, times the derivative of the second. The derivative of 2 minus 2x is just negative 2. Plus the second, copy 2 minus 2x, times the derivative of the first. Derivative of 2x is just 2. Okay, we are looking to maximize the product of areas, which means I'm looking for a place where on the graph of the p function I have a horizontal tangent line, because that's what's going to happen up there at the maximum. Also actually could be one of the endpoints, but definitely we need some critical points here. So we're going to take this derivative and set it equal to 0, which means it's in our best interest to clean it up before we set it equal to 0. So the 2x times -2, that's -4x, plus, and now I'll distribute the last 2 that you see and get 4 minus 4x. And so altogether, I see 4 minus 8x. That's my derivative. And we're looking for critical points, and so we set it equal to 0. And solving this equation is pretty easy. You should see that x is equal to 1/2 in 2 steps. So that's our critical point. Now the fact is, x is definitely trapped between 0 and 1. Could be 0, could be 1, so less than or equal to for both of those symbols. And so this is a standard calculus type problem. Maximize a function. Find the global maximum of some function on a closed interval. And this standard calculus problem has a standard calculus solution, and it's one that we saw recently. We're making a table where we're plugging in the x values into the original function, not the derivative, but the original, which is called p. And the kinds of numbers that we're putting in here are critical points, which is that guy, and endpoints, 0 and 1. And we just plug each of these things one at a time into our original p function. So there's a couple of versions of the p function. I guess I'll use this one here. So when I plug, let's do 0 and 1 first. When I plug 0 in for both of these x's, I get 0 times 2. So that's going to be a 0 right there. And when I plug 1 in for this x, well, for both x's, but when I plug 1 in for the second x, I get 2 minus 2, which is also 0. So 0 times 2 is another 0. So these two are 0. I'm guessing the 1/2 is going to give us our winner. And so we just carefully plug a 1/2 in for both of these x's. 2 times a 1/2 is 1. This is 2 minus 2 times a 1/2. That's also 1. So 1 times 1 is 1. So the maximum product here happens right there. It is at 1. It is when x is a 1/2, and the maximum product turns out to be 1. Okay, and we don't need a sentence to justify that one. We need a sentence to justify when we use a sign test, but not when we do this closed interval maximizing, global maximizing. Okay, number 3. We're given some information about f and g at x equals 3, and then we're going to find some stuff in these different parts. So part A, we're looking for g minus f prime of 3. Okay, this is supposed to be easy because we have a difference rule. We saw this a few classes ago, that the derivative of g minus f is really the derivative of g minus the derivative of f. Sums and differences are really nice. And in this particular case, we're applying that difference rule at x equals 3. And so we just do our subtraction here. G prime of 3 is given as 4. F prime of 3 is -2. So we should get 6. Part B has g over f. So first thing to do is recognize this is a quotient, so we must apply the quotient rule. Now the thing in the bottom of the quotient rule, if you just look at the previous page, was the g function squared. You got to be really careful. You can't just memorize those letters. What really is supposed to go down here is the bottom function squared. The bottom function, it's very mean of me, but I changed it. I swapped the letters f and g from our original presentation of the quotient rule. So you got to be really careful that you don't just memorize the letters, but you've got to understand this rule in English. So it is the bottom thing squared. And then in English, upstairs, we're going to put the bottom times the derivative of the top minus the top, oops, top is g now, times the derivative of the bottom. And in each of these parentheses, we're putting the number 3. We're applying the quotient rule at x equals 3. And now it's just a matter of doing some careful arithmetic. So f of 3 is 5 times 4 minus -1 times -2 divided by 5 squared. So upstairs I see 20 minus 2, which is 18. Downstairs 25, and that's our answer. Part C. All right, so now we've got a complicated function h of x, and we're trying to find the equation of the tangent line of h at x equals 3. Okay, if I am looking for the equation of a line, I definitely need a point and a slope. Let's start with the point. The point happens for the h function when x is 3. So that means that in here, all of the x's become 3's. So 3 times g of 3 plus 3 times 3 squared. And again, now it's just arithmetic. So g of 3 is just off the page here. Copy that one from up above. G of 3 is -1. So 3 times -1 plus 27. So 24, which means that the point of tangency is 3, 24. So we found our point. Now we need to find a slope. So to find a slope, we know that the slope of the tangent line is the derivative. So we're going to first find the derivative of h at x, not at 3 yet. We're not ready to find it at 3. First, we got to find it at a generic x, and then we'll find it at 3. So x times g of x plus 3x squared. First thing to recognize is that this big old plus sign here tells me that I can separate, and I can do two different independent derivatives with a plus sign in between. So I'm going to put a plus sign in between, and I'm going to start with the second derivative. That one's easier. The derivative of this 3x squared is just 6x. So that's the plus 6x that's over there. Now we've got the harder part. So the harder part is finding the derivative of this, but this is clearly a product of something with x times something with x. And so we must use the product rule. First times derivative of the second, that's just called g prime, plus second, that's g copied, times the derivative of the first, derivative of x is just 1. So there is the generic derivative of h. And now that we know that, we're able to plug in the particular number we're interested in for x, which is 3. So carefully just copying all of these x's become 3's. I won't write the times 1 anymore. And now it's arithmetic, 3 times. So now we need g prime of 3, and we're also going to need g of 3 again. So we've got 4 and -1. 4 plus -1 plus 18. I think we've got everything. And so let's see, that's 12, 11, 29. Is that right? So 29 is the slope of our tangent line. And so now we just have to do our mx plus b thing to finish. So the equation of the tangent line, y equals, it's supposed to be mx plus b. We just found that m is 29. In order to find the b, we're going to plug in the coordinates of the point. It's up here in red. So the y becomes 24 equals 29 times the x is 3 plus b. 24 equals 87 plus b. So b is -63. And so then our final answer, y equals 29x minus 63. That's the equation of the tangent line. Okay, number 4 says now we're going to review 3 different kinds of functions. So go ahead and read through this. I'm not going to read that out loud. Number 5 says below are the graphs of different power functions. Write down a possible formula of a power function for each of the given graphs. So remember, power functions are up here, k times x to a power, number times x to a number. Okay, so there's different right answers here, but for example, this top one could be y equals x squared. If you put y equals x to the 4th, that's okay with me too. Really, any positive even power up there is fine. This one is opening downwards, so it's just going to be the opposite sign of whatever we put in the first one. This one looks like an odd power. And I know that because on the left it goes down and on the right it goes up. Because they go different directions, it's got to be an odd positive integer. And this one looks like the opposite sign of that previous one. Down here looks like a square root function to me. It dies out for any negative values of x, which makes sense because you can't do the square root of a negative number, not in the reals anyway. And this one looks like an odd root to me because there you can do cube root of a negative, for example. Okay, and then these last two are similar to each other but quite different looking from the rest. So hopefully we just recognize that this is 1 over, oh, I haven't been following my directions. So it's supposed to make it really look like that, like a power function. So ultimately a number times x to a number. Okay, this one here is a hyperbola. It looks like 1 over x to me. which I should write as x to the -1. And then this one, because both sides are positive, all the time is positive, maybe something like 1 over x squared, or equivalently x to the -2. End behavior is determined by the degree of the polynomial and the sign of the leading coefficient. So let's take a look at this. It says we're trying to find the limit as x goes to infinity and -infinity of f of x, where f of x is this thing. So all we care about for this end behavior business is the power, which is a 5, and the leading coefficient, really just the sign of the leading coefficient, which is a negative sign. And so that means that it is an odd power, odd positive integer. So that means it's going to look like either this x cubed or this negative x cubed. And which one is it? Well, because it was a -7 in the front, it's going to look like this negative x cubed. So what that tells me is that this function, as we go left, goes up, and as we go right forever, goes down forever. So left is up and right is down. And so we'll just fill in our answers. This is saying as you go to the right forever, what's happening to the y value? Well, this function is going down forever. So -infinity has to be the answer there. And as we go, x goes to -infinity, that means go left forever. We saw this function has to go up forever. So that means +infinity. Okay, number 7, it's kind of a long problem here. For this particular function, we're going to find asymptotes, zeros, and holes, and then sketch the function. We're going to follow the detailed process laid out in the reference sheet on the next page, created by former GCC math teacher and a good friend of mine, Lee McGee. So the process is on the next page, so we'll just go through them in order. So step 1 says to factor numerator and denominator completely. I guess I'll number these here. Okay, so we're factoring on the top. The greatest common factor is x, so pulling that thing out first is a good idea. And divided by, same deal on the bottom, pull out the greatest common factor, which is x. And then potentially these things in the parentheses factor even further into 2 new sets of parentheses. Don't forget the x in the, I guess I'll go down a line. Don't forget the x in the front. That doesn't disappear, although it will cancel in just a moment. So 2 new sets of parentheses, something like this. Okay, so on the top, that first thing factors is an x plus 4 times an x minus 3. On the bottom, I'm copying my x, and then this one is a little bit tougher for me because of the 2, but I have confidence that I can figure this out. So we're trying to build a 6. I think we want a 6 there and a 1 there, and that should give us the 13x in the middle. Okay, I like that. All right, and then step number 2 says if there's no common factors, skip to step 4, but there are common factors. And so continuing to read, it says common factors in numerator and denominator represent wholes. The x-coordinates of these holes are the zeros of the common factors. So it says eliminate these common factors, and from now on work only with the simplified function. Substitute the x-coordinates of the holes back into the reduced function to find the y-coordinates of the holes and plot the holes. Oh my goodness, that is a mouthful. But ultimately, we're just looking for things that we can cancel top and bottom. So those factors of x we can get rid of. Be really careful. You cannot cancel x's there. You can't cancel like a 4 with a 2 or a 3 with a 6. Nothing else gets canceled. Just common factors, things that agree entirely with each other. So for example, I see an x plus 4 here. If this was also exactly x plus 4, then I'd cancel the whole things in the parentheses. But we can't do that here, just the x's. So the x's cancel, and we're just going to do the rest of this problem with what remains after we've canceled these x's. But Lee does say that we should be finding the coordinates of the holes. And it says that the coordinates of the holes, the x-coordinate is the 0 of the thing that we just factored. So this one's a little bit tricky, but suppose that x plus 4 was something that we could have factored. We can't here. But if we could have factored x plus 4, then we would figure out when x plus 4 is equal to 0. And that would give us x equals -4. And it would say there's a hole happening at x equals -4. But that isn't the thing that canceled. The thing that canceled was x. And so the hole occurs when x is 0, not x plus 4, but when x is 0, and that equation is already solved. And so to find the location of the hole, we're going to plug 0 into R. Move this down a little bit. Now technically we can't plug 0 into R, because when we plug 0 into R, you really should be going all the way back to the original. And if you plug 0 in for all of these things, you will get 0 divided by 0, which we've seen is an indeterminate form. So maybe I can put like quotation marks around this, like R of 0 does not exist, but I'm going to plug 0 into the simplified version of things, which is right there. So plugging 0 for all of the x's, not the ones that I've crossed off in red, I get 0 plus 4 times 0 minus 3 divided by 0 plus 1 times 0 plus 6. So upstairs I see negative 12 and downstairs is 6, so negative 2. And so that tells me that the location of the hole, the only hole on this graph, is when x is 0 and y is negative 2. And we're going to plot that hole right now by putting an open circle. So the graph is going to go through that point, but technically skips right over it. Okay, so I think that was actually step 3 for following this process. So there's step 3. Step 4, if 0 was not the x-coordinate of a hole in part 3, then plug in 0 for x to find the y-intercept. Okay, so a little bit confusing the beginning part of that sentence, but if I just said find the y-intercept of any function, then you would plug 0 in for x. To find the y-intercept, you let x equal 0. To find the x-intercept, you let y equal 0. So he's saying as long as we didn't have a hole at x equals 0, then we're just going to plug 0 in to find our y-intercept. But we did have a hole at x equals 0, so again, technically we're not allowed to plug 0 in, although we just did define the location of the hole. In any event, in some problems you would just plug 0 in right now and you'd find what the y-intercept is. Maybe it's up here or there or wherever. In this case, it's a hole. That is well, there's no y-intercept, but we've represented as best we can with a hole. Okay, so 4, nothing to do. The y-intercept would be a hole. So it just doesn't work. Okay, number 5, the zeros of the numerator are the x-intercepts of the function. So let's find that. Number 5, zeros of the numerator. So we're not going back to the original. We're instead going to our simplified version, which is right here. So we're just looking for zeros of the numerator. So we'll solve this equation, x plus 4 equals 0. X plus 4 times x minus 3 equals 0, which means solving 2 separate simpler equations, x plus 4 is 0 or x minus 3 is 0. And we get 2 solutions here, negative 4 and 3. And so why is this going to find us x-intercepts? Well, if you want to find an x-intercept, you would let y equal 0. And letting y equal 0 is like letting the function equal 0, right? So we'd let the whole thing equal 0. But the only way to make a fraction equal to 0 is to make the top equal to 0. So we make the top equal to 0 because we're really solving this bigger equation that's written up here. And so that's what we did. We solved the top equal to 0, and we're going to now plot our 2 x-intercepts at negative 4 and 3. So negative 4 comma 0, that's the y, and then 3 comma 0, again 0 for the y. Okay, those are not holes, those are actual points that are on the graph. Okay, next up, the zeros of the denominator are vertical asymptotes of the graph. Plot them. Okay, again going to the factored version, we're looking for the denominator to equal 0. So I'm just going to copy that thing and make it equal 0. And the reason that making the bottom equal to 0 should give us vertical asymptotes is that the way you get vertical asymptotes is to have a fraction that is not defined, which means 0 in the bottom. So we're setting the bottom equal to 0 to force the fraction to be undefined, and these will be the locations of our vertical asymptotes. So again, just like up above, we get 2 simpler equations that we solve. And so, oh, I missed something, 2x plus 1. So here, solving for x in 2 steps gives negative 1/2, and over here, negative 6. And these are the locations of the vertical asymptotes. So how are we going to graph these things? We're just going to put dotted lines. So negative 1/2 and negative 6. So negative 1/2 roughly here, and then negative 6. Those aren't technically part of the graph itself. The function does not exist at x equals negative 6 or negative 1/2, but those things will help us sort of find the skeleton for where the graph lives. It is for sure not going to cross over either of those two dotted lines. Okay, number 7 has to do with horizontal asymptotes. I'm not going to read the whole theorem. Turns out for 7, the easiest place to think about horizontal asymptotes is actually the original function. So right now I'm looking back up here. So to find the locations of the horizontal asymptotes, we are looking for the degree on the top and separately the degree on the bottom. And remember, the degree is the highest power. So the degree upstairs is 3, and the degree downstairs is also 3. And depending on which one of those numbers is bigger, that dictates what kind of horizontal asymptotes you have, if any. In this case, they're exactly the same as a tie. The degrees are both equal to each other. And when it's a tie like this, the horizontal asymptote happens at y equals the quotient of the leading coefficients. And so I'm going to put in the invisible 1 that is the leading coefficient on top. And so the horizontal asymptote in this case is y equals 1/2. And so there's not really a whole heck of a lot to write down here. It's a lot of thinking about things like I just discussed there, but the horizontal asymptote with a lot of thinking and not much writing is at y equals 1/2, and we're going to plot that in the same way as we plotted the vertical asymptote. Let's do this in a different color. Okay, and so we'll plot y equals 1/2 as a dotted horizontal line. It's perfectly okay for the graph to cross that line. But as we approach the far right and far left of this graph, our graph is going to approach that line, that dotted line. Okay, next up, it says we're going to skip this step. It talks about finding like a crossing point, like where does the graph that we haven't yet drawn cross that horizontal asymptote. It's totally fine for us to skip that. Now we're going to make a sign chart for the function, which includes all the x-intercepts and all vertical asymptotes, and the sign chart is on the original function, no derivatives here. In fact, no calculus anywhere in this question. This is a pre-calculus question. So, sign chart. Let me copy the factored version of this thing. So it's up there in black. Okay, so there's our factored version after we cancel those leading x's. And what we're going to do is make a sign chart on all of the x-intercepts and all of the vertical asymptotes, which really means just any place that makes any of these 4 factors equal to 0 goes onto our sign chart. So the numbers that we see, we found them up above, but x equals -4, x equals 3, x equals -1/2, and x equals -6. Only thing we have to do is put them in the right order on our sign chart. So the smallest one is -6, and then -4, and then -1/2, and then finally +3. Makes absolutely no difference whether or not these things are spaced appropriately. We just need to get them in the right order. And we label every sign chart with the function that those numbers came from. And all of these numbers came from r of x, not r prime, just r. Okay, and now we're doing a sign chart, which means picking a number in each of the 5 intervals that we see, 1, 2, 3, 4, and 5, plugging one number from each interval in for every single one of those x's and recording on this graph the sign of r of x. This is actually pretty easy to do once you get the hang of it. We're going to pick a number out here, for example, x equals 100, and we're going to plug 100 in here and here and here and here. Again, I don't actually care about the arithmetic or the final answer other than its sign. So all I'm going to do is record the signs when I plug x equals 100 into each parentheses. So the sign of this thing right here when x is 100, it's positive, right? I mean, it's 104. I don't actually care that it's 104. I just need to know whether it's positive or negative. Then I plug x here and I ask how much is this? Well, it's 100 minus 3. You don't need to do the calculation. You just need to know that's positive, right? Doesn't matter that it's 97. It matters that it's positive. Plug x equals 100 here. This thing right here for sure is positive. And then finally, when x is 100, this thing is also positive. So when I divide and multiply all these 4 of these positive signs, I get a positive at the end of the day, and that's all that we care about. Okay, next thing is in this space right here. 0 is a convenient number to plug in. So we plug 0 in here, and this thing is positive. I plug 0 here, and this thing is now negative. So that's my first change. In fact, spoiler, that's going to be my only change. And then I'm plugging 0 in here, and this is a positive, and I plug 0 here, and that is positive. So the whole thing, I see 1 negative and 3 positive. So when all is said and done, that is a negative. And then we play the same game 3 more times. So let's pick a number in this space in here, for example, -1. -1 here gives a positive there. -1 here, that one's a negative. -1 here, this one changes. And again, that's going to be the only change. That's a negative. And then -1 here, this is still a positive number. So now I've got 2 pluses, 2 minuses. Altogether, it is a plus. And I'm just going to skip ahead to the answer here, and I will say that this is a minus and this is a plus, but you should verify those using the same sign chart idea calculations that we've been doing. Okay, and now the hard part is to sketch the function. Like all we have here is that it's plus, minus, plus, minus, plus. Okay, let's see if we can do this. Lots of talking and very little writing. All right, at the far left-hand side, it was plus. And then it becomes a minus when we hit -4. When we hit -6. So it's plus on the left of -6 and then minus just to the right. So let's do this in black. Okay, it's positive to the left of -6. All right, here are your choices. You have to for sure get really close to the horizontal asymptote. So you could get close that way, or you could get close from below. And the other thing you need to do is not change sign anymore. And so this function right here would naturally continue down. Maybe I should take a step back. You also, to the left of this red vertical asymptote at -6, have to get really close to that asymptote as you get close to -6. And so the choice is either that or this guy has to come down here. And how do I know which one it is? Well, if it were the bottom one, then I would have found another x-intercept, and I didn't. And in fact, the bottom one is negative over here. The y values are negative, and that's no good because we discovered that this function is supposed to be positive everywhere to the left of -6. So it's got to be that top one. And so by process of elimination, we pick the top one. So it gets very close to the horizontal asymptote at the far left and very close to the vertical asymptote up towards positive infinity. And then it says between -6 and -4, the function is supposed to be negative, and then it's supposed to hit that orange -4. We've got an x-intercept right there. So we need to be negative to the between -6 and -4, and we're going to hit that orange dot. And so how are we going to do that? Well, again, we've got vertical asymptotes. So you could either have gone towards the vertical asymptote that way or this way, but only one of them is negative. And so again, by process of elimination, you pick the right one. The right one is down here. Those are negative y values, but that one up there were positive y values. So we're going to come in very close to this asymptote. We're going to hit at -4. And then continuing to look at the sign chart, between -4 and -0.5, this function is positive. So we're going to change signs now. We're going to go right through the x-axis and we're going to become positive. And again, I will say either it needs to go to that red asymptote like that or like that. But if it were going to have turned around, then we would have found another x-intercept and we would have had some negatives down there. But we know we're supposed to be positive the entire time, so it's got to be this one up here. So again, it's just like a lot of analysis and then process of elimination. And I mentioned before, but I'll point out again, it is absolutely no problem for the function to hit the horizontal asymptote. Some students have a misconception that functions can never hit their horizontal asymptote. That is simply not true. If you really wanted to know where it hits the horizontal asymptote, you can do step 8. That's one that we skipped, but it's okay with me to not do that. Okay, so moving on to the right of -0.5 and left of 3. So between -0.5 and 3, the function's negative. So here we go. We got to be really close to this red vertical asymptote. We could either have gone up to positive infinity or down to minus infinity. Which one is it going to be? Well, it's got to be negative the whole time. So it's got to be the bottom one that I drew. And additionally, it's got to hit our hole, that blue circle there. So it's going to be kind of tight to draw this in here, but it's coming this way. Hits the hole. Should not have actually entered the hole. Let's go back. So it hits there, continues up. It's got to hit that 3. It's really hard to draw this kind of accurately because I haven't given myself very much room here. I'm actually going to give myself a little more space with this vertical asymptote. So pretend that's at -0.5. And so the idea here is that this function is going to hit the x-intercept. It's going to hit the hole at the y-intercept, but it's just going to go right through. There's no change in behavior at that hole. It just goes right on through. It's just a point that isn't there, but the behavior of the function is quite ordinary near that point. Okay, and then finally, the far right, we see a plus sign. And so this function is going to be positive forever and ever from here on out. But at the same time, it has to get really close to this horizontal asymptote at the far right of the graph. And so I think it's just going to very naturally approach it from below. Technically, it could, like it could do something kind of wonky. It could come up and then level off down there. There's really no way at this moment for us to know whether or not it does that. So we're going to assume the simplest possible behavior when we graph our rational functions. And just because that one was so darn tough, we'll check our work real quick. By plugging in the original function. So I like to go to the original form of the thing. So big parentheses here, x cubed plus x squared minus 12x, close parentheses divided by open 2x cubed plus 13x squared plus 6x. So I think that's good. I'm not going to do the standard window here. I'm going to do a window that's appropriate for what we discovered. So it looks like there's action here. -10 maybe is okay, but maybe we'll cut it off at like 7 or something like that. So -10 to 7. And then for the y's, definitely got to include this -2. And we should include this positive 1/2 up here. So I don't know, -5 to 5. See how that looks. And so what we expect to see is this first piece going up, vertical asymptote, and then it's going to come through, hit at -4, go up again, another vertical asymptote, and then just barely getting over the axis there. It's kind of hard to see that part. So let's just look between like 0 and 1/2, just to see that the horizontal asymptote here at the far right. So we're missing a lot of the behavior here because I've got this zoomed in version of things, but we expect to see it level off at 1/2. Actually, probably don't quite see enough there in terms of leveling off. Let's go from like 0 to 20. Last look at this one. So 1/2 is right here in the middle, and we expect to see this graph level off at its horizontal asymptote of 1/2. Is 1/2 not in the middle? Well, 1/2 is at the top. Great. So it's actually supposed to be leveling off at the top, and the farther out you go, the closer we should see it get to the top of this window. That should convince us that indeed 1/2 is the horizontal asymptote. All right, so those rational function problems are tough, they are long, they are involved, but they are good stuff. Practice with them.